Hello, let's take a look at a few more examples of proof by induction. We will prove that every natural number n is either even or odd. We enter the tactic mode. We apply the induction tactic on the natural number n. Let us handle the 0 case first. We have to prove that 0 is an even number. We already have a proof for this, so we will simply reuse this. In the successor case, we have access to the previous number n and the inductive hypothesis for n, and we have to prove that n plus 1 is either even or odd. Since the inductive hypothesis is an OR, we will split the proof into a proof by cases. In the left case, we have that n is an even number, and we can conclude that n plus 1 is an odd number. Using the already proven theorem that the successor of an even number has to be an odd number. So we supply the proof En, which stands for n is even, to finish this case. In the INR case, we have that n is an odd number, and we can conclude that n plus 1 is an even number. And this finishes the proof. Let us go ahead and prove a more complicated theorem. We will prove that every natural number can be written as a multiple of a power of 2 and an odd number if the number n is greater than 0. So we will try to apply strong induction on the natural number n here. Observe that in the conclusion there is no mention of n, and in the hypothesis too there is no mention of the fact that n is equal to 0. We can fix this problem by applying modus ponens. The theorem modus ponens is that given a proof of P, where P is some proposition, and a proof of P implies Q, where Q is some proposition, we can conclude Q. Given this, we can apply modus ponens with our hypothesis Hn here to rewrite the goal into an implication involving n on the left hand side. Now applying strong induction leads to the implication with 0 greater than 0 in the base case. This can be easily proved using the omega tactic. In the inductive case, we introduce the smaller number n, the inductive hypothesis for the strong induction, and the fact that n plus 1 is greater than 0, which is the antecedent of the implication that we are trying to prove. We split the proof into cases depending on whether n plus 1 is even or odd. In the INL case, we have n plus 1 is even, this is a non-trivial case. In the INR case, we have that n plus 1 is odd. This case is trivial. We will leave the INL case for later and go ahead and prove the INR case. In the INR case, we can set k to 0 and we can set m to n plus 1 and use the facts in the hypothesis to conclude the theorem. We have to introduce the hypothesis of INR using a binding H. Now we have to prove the right hand side of the AND. So RFL does not work. We have to do a rewrite to convert 2 power 0 to 1. RFL still does not work. So let us rewrite 1 times n plus 1 into n plus 1. And that finishes the easy case. We can combine multiple rewrites into a single rewrite using multiple theorems like so. Let us go ahead and prove the INL case. We have the hypothesis H, which is that n plus 1 is even. We can use the hypothesis H to obtain a number such that n plus 1 is 2 times that number. So let us name it K and the corresponding equality as HK. In fact, let me rename K into something else to avoid confusion. We can now apply the induction hypothesis to W to express W as a product of a power of 2 and an odd number. So we need the fact that W is greater than 0 here. This can be obtained using omega. Now we apply IHN with W and the proof that W is greater than 0. We also need the fact that W is less than or equal to N. So the omega tactic should be able to determine this here. So we can inline both applications of omega, one to conclude that W is less than or equal to N, the other to conclude that W is greater than 0. Now H prime is the inductive hypothesis applied to W. Observe that we have to extract this K and M from H prime. So for this, we use the pair syntax to extract these components from the proof of there exists, which is H prime. Notice that HK is still there exists, so we have to do one more pair extraction. And we can do this in line here. Since HK is a proof of there exists, we can split it further into the existence of an M and a proof HM. Observe HM is just that M is odd and W is 2 power K times M, where K is some natural number. We are now ready to make progress on the goal. So we substitute K plus 1 for the K in the goal, and we substitute M for the M in the goal. So the goal does not have any there exists quantifier now. Let me show you this. We have to prove that M is odd and N plus 1 is 2 power K plus 1 times M. So we use the constructor tactic to prove both cases. In the left case, we already have the fact that M is odd in the hypothesis as HM dot left. So we use exact HM dot left to conclude this. And in the right case, we have to perform a series of calculations to conclude that N plus 1 is 2 power K plus 1 times M. So we will use the hypothesis HW here. So we can write N plus 1 as 2 times W by HW. We can write 2 times W as 2 times 2 power K times M using HM dot right. And we can write this as 2 times 2 power K times M by associativity of multiplication. And finally, I can rewrite this as 2 power K plus 1 times M using the rule for multiplying powers. This rule is called power underscore sub, which is the theorem n power m plus 1 is n power m times n. So we have to do this rewrite from right to left. So we specify \L here. This still does not work. Because the Pau_Sugg theorem requires 2 power k times 2 and not 2 times 2 power k. This can be fixed by using commutativity of multiplication before applying this theorem. And now we are done. So observe how the commutativity of multiplication rewrites 2 times 2 power k into 2 power k times 2, and then the Pau_Sugg theorem rewrites that 2 power k times 2 into 2 power successor of k. In the theorem statement, we need not have m in the hypothesis since it's existentially quantified. And that has finished the theorem. Thank you for watching. Bye.